In this lecture, we're going to introduce inductors and capacitors and do a little bit of review. If you've watched previous videos, you've seen the discussion on inductors and capacitors. I want to do some review and a couple of example problems. So first, let's look at the capacitor. The capacitor has a symbol of two parallel plates. It has a capacitance. The units for capacitance are the farad. In reality, most capacitors have units of microfarads and below, so very difficult to fabricate and get a farad capacitor. There is, like all elements, of voltage and a current associated with the capacitor. The difference between a capacitor and the resistor is that there is a derivative relationship between the current and the voltage. So I is equal to the capacitance C times dV dt, the time derivative of the voltage. The capacitance is a function of geometry. In other words, what is the physical size of the capacitor? What is the area of the plates? What is the distance between the plates? And it's also a function of the material that is between the plates. And capacitors can store energy. And in fact, that's one of their main uses, is to be a temporary energy storage element. And they store energy in the form of an electric field. So they store energy. And at any given moment, the energy stored is 1/2 CV squared. Okay. So that's the energy stored in a capacitor. Now I want to point out that because of this time derivative relationship, this means a couple of things. Okay, first of all, it means you only have current in a capacitor when the voltage is a function of time. So under DC conditions, in other words, if the voltages and currents in a circuit are DC, then dV dt is the derivative of a constant, and that goes to 0, which means the current in the capacitor goes to 0. And so under DC conditions, capacitors look like open circuits because they have 0 current. And they behave like open circuits in the circuit. Okay. So if you have a constant voltage, you will not have a current in your capacitor. The other thing is that capacitors have what we refer to as initial conditions. In other words, they have it's possible for a capacitor to sit, if it's not hooked to a circuit, for very long periods of time and hold a DC charge. So capacitors have the ability to have initial conditions. And let's look mathematically at this equation again. Notice that dV dt, what that means is you cannot have an instantaneous change in the voltage in a capacitor. Because if you did have an instantaneous change, the derivative would go to infinity and become undefined. So the voltage on a capacitor cannot change instantaneously, it has to change slowly. You might think of this as being analogous to a water tank holding water. If you open a valve, what happens is the level of water in the tank, the amount of potential energy that it has, drains away slowly. So you don't have like instantly the water is gone. It has to release that stored amount of water. So capacitors are storing a voltage. If you try to get them to instantaneously change that voltage, they'll do everything in their power to resist that. including self-destruction. So you never try to short out a capacitor that's got a voltage on it. That'll create a catastrophe. So two things then. Number one, under DC conditions, the capacitors look like open circuits. Number two, capacitive voltage can't change instantaneously. Now we can take this equation, I equals C dV dt, and if the voltage is known, we can calculate the current from this equation. Now let's suppose you don't know the voltage. Let's suppose you know the current. Then you would need a way to solve for V. So what we can do there is play around with this equation by playing a little loose and fast with the mathematics. And so what we can do then is we can say dV is 1 over C I dt, and now we can integrate both sides. So if we do that, this goes from V at some initial condition to some V of t, and this goes from t equals 0, we'll say. You have to have a starting point. In order to get an equation, it's got to be a definite integral to some t. So basically then what I get is, on the left-hand side, I get V of t because it's a perfect differential, minus the initial condition on the voltage is the integral of 1 over C, or integral of C I dt. So if the current is known, then I can integrate that and I can solve for V of t, 1 over C integral of I of t dt plus the initial voltage. Okay. So these two equations, A and B, give us what we need. Let me get rid of that little, sometimes this device does this. Give us what we need to solve for current given voltage or voltage given current. Alright, so let's look at a couple of examples. Typically, capacitor voltages are either exponentially decayed or sinusoids or a combination of the two, or maybe they're functions of time. Maybe they're like functions of t. And that's just from the physics of circuits that you're more likely to see those functions. So let's suppose we have some capacitor voltage, V of t is given by 3e to the minus 2t. And what we want to do is find I of t in the capacitor and find the energy stored. And let's do it at 0.5 seconds for that energy. So first of all, and let's say this is a 3 millifarad capacitor. So I is C dV dt, so that's 3 times 10 to the minus 3. And then when I take the derivative of that exponential, I get minus 2 times 3 e to the minus 2t. So let's see, if I multiply through, that is minus 18, 10 to the minus 3, e to the minus 2t, or 0.018 e to the minus 2t, and that would be in volts. Sorry, in amps. Okay, so there's my current. Now if I want to find the energy, I use the equation E is 1/2 CV squared. And so plugging in V, I get 1/2 times 3 times 10 to the minus third. V squared is 3e to the minus 2t squared. So that's 1.5, 10 to the minus third, and then inside the brackets I have 9e to the minus 4t. If you need to review properties of exponents to remember how to raise an exponential to a power, basically the exponent and the power multiply. Okay, so that gives me a final result of 13.5, 10 to the minus 3, e to the minus 4t. And I asked for that at half a second. So e 13.5, 10 to the minus 3, exponent to the minus 2 when I plug in 1/2 for t. 13.5, 10 to the minus 3 over e squared. And I will let you grab a calculator and determine e squared. Remember, e is your exponential value of like 2.67, give or take. And so you just plug that in, square it, and do the division. Looking like this will be about 1.5, and the energy here is going to be in joules. Okay, so that would be the energy at half a second. This is the energy as a function of time. So when we talk about inductors and capacitors, things are going to be talked about in terms of function of time. Now let's look at capacitors in series. So C1 and C2. So I'll have some V1 of T and some V2 of T. So the first thing I want to say is that voltage divider across capacitors is not quite the same as it is in resistors, because capacitors can have initial conditions, and depending on how the circuit was built and configured before you put the capacitors into an active mode, in other words, put them in the circuit, V1 and V2 may not be in a voltage divider type ratio. So you cannot automatically assume that you have a voltage divider relationship. So in this particular situation, if you wanted to find V1 and V2, the thing that you have to do is you have to do an equivalent capacitance. So here's V, and here's I. And so here you could use your relationship I is C dV dt. Once you have that, you have this total voltage. Rather than using voltage divider, you can come back to this equation where V1 of t will be the integral of I of t dt plus V1 of 0, and V2 of t is the integral of I of t dt plus V2 of 0. Okay, so a problem like this, depending on your initial conditions, you may very well have to use this approach to finding V1 and V2. Now let's determine how to find an equivalent capacitance. So let's say we have two capacitors in series. Let's let this be 1/2 of a farad, and let's let this be 1/4 of a farad. So capacitances combine in series like resistors combine in parallel. So here's our C equivalent. So 1 over C equivalent is 1 over C1 plus 1 over C2, which if we look at these numbers in this example, 1 over C equivalent is 2 plus 4, or 6. So C equivalent is 1/6 if we wanted to use the product over sum rule for 2 at a time so that we didn't have to do this inversion, that would work as well. Okay, so that's an example of how to combine capacitors in series. Let's look at a situation where we're given a current and an initial condition on the voltage. So we'll let, sorry, I need to lock this where it doesn't rotate. Let's let I of t be over. Let's let I of t be, let's go ahead and let it be 3t. Okay, we'll just make it simple. And it'll be in amps. And then let's let the capacitor be, we'll make that simple too, even though I told you there's no such thing as a farad capacitor. In the real world, we'll use it because it simplifies our calculations. And we'll give it an initial condition of 2 volts. And let's say that, yeah, that looks good. Okay, so V of t, according to our equation, is 1 over c, the integral of I of t dt plus v at 0. So that's going to be 1/2 the integral of 3t dt plus 2 volts. So that is 1/2 3t squared over 3 plus 2 volts, or 1/6, actually 3/6, so 1/2 t squared plus 2, all of that in volts. So you can see the voltage is going to be a function of time because the current was a function of time. And up here in the first example we worked, the current was a function of time because the voltage was a function of time. Okay, so that's a couple of examples